Hi everybody. So you can see there are 3 names here, and there are obviously 2. It's not a mistake. So I'm going to first start to introduce the missing person, which is Neil Thornbrae. He's in Palo Alto. He's part of Criteo as well, but he's right now in Palo Alto. He couldn't attend because we have an annual summit like in 2 weeks, and he couldn't come like twice in Paris due to obvious family reasons. But Neil did. So Neil is a dev lead at Criteo. He's leading our new warehouse architecture in Palo Alto, which is some kind of an innovation team around building data stores and stuff like that. Neil's been working in Amazon and formerly in Oracle, so he knows a bunch of things about databases, and he wrote all the data generation tools we have and we are using in this presentation. So the second person is Pavel Jostek, which is here. Pavel is an engineer in my team. He's working previously at CERN and is a hardcore coder, and most of the good code that's behind this presentation has been written by him. The bad code's been written by me, or what remains of the bad code. And me, I'm François Jehl. I'm the lead of the data storage team in the analytics group at Criteo. So what we do is we provide data stores and for analytic data. So for example, we take care of Hive. We have a bunch of Vertica clusters that both have users and applications. We also have MySQL instances for small things, the datastore and stuff like that. And we're also testing new fancy things to play with. Bare metal, not in the cloud, which is another discussion. So what's all this about? So when I started this presentation, I was trying to pick some marketing material from Criteo, because you have always to explain like what does Criteo do. I mean, they put ads in your web browser, but besides that. So I tried to take the marketing slides, but there are too much people like looking at screens with fancy graphs, so I tried to build one myself. So what's Criteo from my point of view? So we have people. What do people do? They navigate on websites. And the websites are clients. And so when they navigate on websites, such as when they see products, like we get some information. Our clients send this information. And so we get that, and we put that in our Hadoop cluster via Kafka and all that stuff. And then those guys, they maybe go to some news website. And we display ads there. And maybe they click on the ad. And if they click on the ad, we get some information. And they might also, so when they click on the ad, they get redirected, and then they might buy the product, and we get also information. So, of course, we're selling ads to advertisers, which is obvious, but we're also selling information, which nobody knows really, but we do that. I mean, our advertisers, they want to know the performance. Like if you go, this afternoon we have some meetups in some small meeting rooms, you'll see written on the walls like performance is everything and stuff like that. But I mean, when you want to sell performance to people, I mean, you need to prove that actually there is some performance, so you need to show some figures. I know this is ugly. I mean, just after this GL thing, I'm kind of ashamed. I mean, working backend, and what is this? So the title is Distinct User Count Report. So why is this important? Because one of the metrics, of course, the advertisers are interested if you sell them like a lot of clicks. Like, you see the number of clicks. But most people, if you read like the advertising papers, would say, like all those clicks always come from the same users. You don't have that much people coming to your website. So we need to show that it's not the case. Like you have many people coming to your website, which in the end translates to counting user IDs. And when you start seeing counting user IDs at Criteo, everybody saying, oh shit. Because that's the worst thing that can ever happen, is counting user IDs. Because we see a lot of them. And of course, our data doesn't flow in by user IDs, like flowing by time. We have time series with user ID, and you need to count distinct values of that. Second bad thing. Initially, the application that was doing that was a crappy tool that was doing the job, just like 3 pages. And like, okay, we are computing count these things on like 2 dimensions and static. Yeah, it was cool. I mean, what we did was like pre-computing the count these things, full C# tools and then Hadoop jobs. It was working. And then, I mean, you want to look fancy to your clients, then you design a new application. And even internally, you design a new application. And you want that to be dynamic, like you want to add new metrics and you get new business, which means every time you alter the data model, since distinct counts are like unassociative by default, you need to recompute all of that. In the end, you start counting and you say, okay, I'm computing count distinct and pre-computing that all the time, that might be a better solution to this problem than creating a new job that computes count distinct for every new use case that I encounter. And then you start reading some papers and say, oh, there's this thing called HyperLogLog that's supposed to bring some kind of associative but approximate, slightly approximate count distincts. I mean, that might be the solution to our problem. So what's HyperLogLog? It's like data structure that brings some associativeness to count distincts. Yeah, okay, that's cool. So we're using Vertica, as I told you. So we're using Vertica, so we took a look at documentation and say, oh, great, they have HyperLogLog, so you can use that. Bad thing is, our ETL pattern, so computing all of that, we usually do that in Hadoop. I mean, we're using Vertica for like Hadoop reporting. We don't like to have long-running, IO-intensive, CPU-intensive jobs on Vertica. So we're like, would like to use that, but you know, like pre-compute those structures in Hadoop and then use the distinct count in Vertica. So we got in touch with Vertica. It told us that for some obvious reasons, it was not available in Hadoop. So we say, okay, this is difficult to code. So I started that, so it's not difficult. So HyperLogLog, French thing, written by a guy, no, not only French, but I mean the main contributor is French. Flageolet. You can read that, that's public. So a bunch of interesting things, but what's the intuition behind HyperLogLog? So if you have a set of values and you don't know how many values there are in there, the likelihood to see an extreme value in this set is slightly correlated to the number of distinct elements. What do I mean when I say that? I mean, like, for example, I get some values, I don't know how much, I like hash all of them, and I show you this precise value that has a lot of zeros, and if my hash is properly distributed, blah, 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 you can see that if I see a value with so much zeros, there might be a lot of them in this set. That's the intuition. For example, if someone didn't tell you how much times he threw some dices, and it tells you, at some point I got 666, you're like, oh, you might have thrown that a lot of time, or being lucky, but we're not talking about luck here. That's the intuition. So, in this case, we might only need to know, like, the maximum number of leading zeros we encountered in this whole set to have an idea of the cardinality. Actually, this is true. So you can read the papers if you want the real proper demonstration. Don't do that. There are links, all that in presentation. And so HyperLogLog was just built on that, and you can estimate that. So what's this structure I'm talking about? Like talking about you need to pre-compute a structure that brings this associativeness. So this is my data. So all logs are way bigger than that, but simplification. So we have 5 lines, pretty easy. So what do? So we have those user IDs that came in and they're associated with the client. So we perform some kind of hash. We don't use 8-bit hashes. I mean, I'm not that old. The only reason why is because it's like it fits on the slide. Okay, so we're using 64 bits, of course. We're using a mirror hash. And so what we do is we define like the precision of the algorithm by splitting data in buckets. So we like randomly take a few bits in the beginning of the hash. Here I took the first 4 and say, okay, I will split the data in those first 4-bit buckets that I convert in decimal there. So this is the bucket of this one. Is in bucket 8, is in bucket 4, is in bucket 12, bucket 3, bucket 6, depending on the value. And then I will compute one thing, which is the leftmost zeros that are left after I remove the bucketing bits. So after that. So I see that this guy has no leading zero, this guy has 1, this guy has 1, this guy has 1, and this guy has none. Okay, perfect. And now I want to aggregate that at the user ID level. And so I store that as an array. I just say that for client ID 1, this guy in bucket 4, I'm 0 indexed. I put a 1 here, bucket 12, put a 1 here. So for client 1, I have because it's initialized in 0, I have an array with like only zeros and 2 ones. And client 2 is the same thing, 3 is 1. And so I have summarized my data set as an array of digits, let's say. And so how does it work? Oh shit, how does it work? So I have this. So I have the raw HyperLogLog estimate. There's like one page telling you like what's the intuition, and then it codes like 10 different papers. And recursively, if you walk this tree, you might understand all the mathematics behind that. I won't tell you anything about that. Like can read the PDFs if you want. So the basic idea is that, so why did we do this bucketing in the first place? It's because if we didn't do the bucketing, we would have some bias. So we split the data in buckets to avoid the bias. And then when you split data in bucket, what do? Usually you do an average on the buckets. So we are going to do an harmonic mean and not an arithmetic mean, just because we are snob. I don't know if say that. Not only, but that's not the main reason, but that can explain that. And then we use a constant. So this is the average. We have this constant, and Pavel is going to talk about that a little bit later. And we multiply also by the square of the synopses cardinality, which is 16 here. And then we applied that, and we computed that, which was the first version, and we used that, like in Vertica, and on top of our data. And for big cardinalities, it was, yeah, great. That's very good. And then, even for this presentation, you remember I have 5 lines. I estimate the result. So it says that I have 12 in both cases, number of user IDs in 5 lines for 2 clients. So it's very bad. So for 5 lines, it's very, very bad. And trust me, for like 1,000 lines, it's also very, very bad. So at this point, I was like, okay. And then Pavel joined. And since he's smart, I told him, yeah, make that work better. And he's going to talk to you about that.
Okay. Thanks, François. Okay, so as just François said, you get these estimates where you expect 2 or 3. Well, this is not entirely true. Actually, the numbers you get are much worse because this is only the harmonic mean, but then you multiply that by alpha m and m. So in the end, you'll get an estimate of a couple of thousand, while you only had three different elements. So maybe it's not that great. It's not something that you expect. Ça marche? Voilà. Okay, so here's a proof. If we set all the buckets to 0, okay, and then we substitute here in this formula with 1, you will get 0.7 m, where m is number of buckets. So if you had 12 bits of precision, then you had 4k buckets, so you would get an estimate of around 3k for no elements. You know, you have nothing and you get 3k. Maybe this is not what you expect. It's an artifact. So, you know, HyperLogLog is huge. It's enormous. It's really cool, but only for the higher cardinalities. If we go to lower cardinalities like 0, then it starts to behave badly. So we implemented a couple of improvements. But before I set off, I just wanted to say that these are not our ideas. We didn't make them up. We just read a couple of good papers from Google, Druid, Facebook, okay, and we just compiled that into one implementation. So yeah, we didn't make it up on our own. Okay, so let's come back to the example that we had that François presented. So we had 2 customers and 5 users. Okay. So for lower cardinalities, we'll apply something which is called linear counting. It's a formula proposed in the original paper by François Jehl. So what it does, it looks at the original buckets that we had for HyperLogLog. So we don't have to scan again the data. We don't have to have another data structure. We just take what we had and we apply another formula. So the formula is actually pretty simple. You just take number of your buckets, okay, and you multiply that by a binary logarithm of this ratio of number of buckets to number of buckets set to 0. So here we have 14 buckets set to 0. Here are 15 buckets set to 0. And in the end, when you compute these numbers here, you get something pretty reasonable. Now it's 3 and 1.5, so we have 1.5 user. Okay, but still it's better than 3k, okay? You agree. So we kept this idea. We implemented that in our Vertica user-defined function. So you see, now we have something for really small cardinalities. We have something for really huge cardinalities. We miss something in between. So there is still a range where both HyperLogLog and this linear counting behave so-so. Okay, so to switch, I forgot to say, to switch between linear counting and other algorithms, we just use an array that we got from a paper, from this Google paper, and we just embedded that in our code. Okay, so what do we do in between, in this middle range cardinalities? We have something which is called 6 neighbors interpolation. It's also taken from Google. So we calculate the estimate. We have an array of estimates. We have an array of biases. That's in the Google paper, so we've taken that and put in our code. So we look at the estimate we have. Then we look at 6 nearest neighbors to that estimate, and then look in the other array to see what are the biases for those estimates. And then we calculate a median of those biases. Okay, and this bias we subtract from the original estimate, and like this we get something more accurate. Okay, so to summarize, in the end we have not one algorithm, but 3 algorithms. We have HyperLogLog, we have linear counting, we have this HyperLogLog with bias correction. So here on this plot that we've taken also from Google, thanks Google, you can see median relative error on the Vertica axis and cardinality on the horizontal axis, while those curves here stand for different algorithms. So the red one is raw estimate. You see that here in the lower cardinalities it's really bad. Then there is linear counting that at some point, starting from here, has much better performance. And somewhere here, it has much better, but still there is this bias correction that is even better. But somewhere here, these 2 curves cross, so then we switch to linear counting. So we have those 3 ranges, and we switch from one to the other. And here you can see what are the conditions to switch from one algorithm to the other algorithm. Okay, so if there is someone in the room who read the original paper, he might or she might raise her hand and say, but wait, in the original paper from François Jehl, there is some large range correction. And did you implement that or not? So in the original paper, they used 32-bit hashes, okay, hash functions. And in our implementation, we use 64-bit hashes. Oops, sorry. So like that, we don't have, well, we expect we won't have any hash collisions. They, of course, might happen, but it's very unlikely. We have to reach cardinalities of 10 to the 19th. We hope it won't happen, or, well, then we'll increase number of bits, but for the timing, it's not the case. So just to clarify, we didn't implement that improvement. All right, so that was for different kind of corrections. Now we have to serialize the synopses. You know, all those buckets that we just calculated, we have to store them on drive or in the memory. So by default, we support 4 bucket sizes. First of all, we support 8 bits. So the buckets are, in fact, you need only 6 bits to store a bucket, okay? Because you have a hash function of 64 bits. So then when you count zeros, it can be 64. So you can use 6 bits to store numbers up to 63. We hope you won't get only 0, so we can use 6 buckets. 6 bits. Initially, we implemented 8 bits to serialize all those buckets because that was very easy to do. But there is some wasted space, okay, because you don't need 2 bits per byte. Then we implemented also 6 bits. There is no wasted space. And we also thought about implementing 5 and 4 bits way of storing the buckets. The only problem is that if your cardinality reaches 2 billions or 32K, you might lose some data. You might lose some number in the bucket. If the number in the bucket is too high, you would just cut it and store as this. So that would suck, clearly. But what we actually do is something that is called offset serialization. So if you think about those hash functions that are, equally distributed, you may think that all the buckets will have similar values. Because when you look at those, maybe I showed this thing. Yeah, so here we have 8 buckets. So, after a certain number of items, you expect to have more or less the same numbers in every bucket, okay? So in this presentation, we don't prove this is really the case, but if you want, you can look in this very gorgeous papers. Yeah, and it's in French, so encrypted. So yeah, instead of storing just buckets like they are, we implemented a method which is called offset serialization. So among all those values, we find the lowest one, which is called the offset, and then we subtract the offset from all the buckets. So if you look back, we had 10, 12, 14, and so on. Then we subtract 7 from all the buckets, and we have 3, 5, 7, 2, and so on. And like that, we can store this offset and the values using 5 or 4 bits, effectively gaining some space. Okay, so like that, we gain space for storage. But of course, it takes more time to compute that because you need some bit twiddling, and yeah, maybe it's not so obvious. All right, so depending on how many bits we want to store, we either use this array, very simple serialization of whatever we have in the bucket, or for 5 of 4 bits, we use this offset. So we find the offset value, we subtract it, and then store these values together with the offset. Okay, so François, you want to talk about?
So yeah, I'm doing my chef again. So once we had that, it was back in February or March. We had this working, so it's okay. So we're going to integrate that in the fancy, not really like the drawing I did, but in the fancy application that's supposed to show those figures. So so one of the things I told you previously is that we need to integrate that into Hadoop, because the synopsis creation, like all the things Pavel presented, will be in Hadoop. And of course, we need to integrate that in Vertica. So in Vertica, in fact, actually that's pretty simple. They have the C++ SDK. They have as well Python, R, and stuff like that. SDK, we wanted to use the most powerful thing. And so we just used their C++ SDK, which is well documented. I mean, and there are a bunch of examples. It was pretty easy to wrap the library within their SDK. So we implemented like 3 user-defined aggregate functions. So one to create the synopses, even if we don't use that in production, because it's mostly done for testing. One to combine 2 synopses together, and one other to perform the actual distance count on synopses. For those who want to start using their SDK, like all the examples are pretty good. The only thing we discovered that was pretty much missing is this parameter that you can write down, the minimus call count, which is by default Vertica will call one of your aggregate functions with the business logic as many times as there are rows instead of grouping by, this is an aggregate function, so we would expect to have 1 call per group by key, and that's not the case if you don't use this thing. If you look for this value in Google, you'll find the information. So we've open sourced that. That's on Criteo's GitHub. Vertica HyperLogLog, because I couldn't find a funnier name. And so, yeah, and on the ETL side of things, so the way we work with Vertica is not the most straightforward. I mean, if you read interviews of people that use Vertica, they also generally use it for their ETL processes. In our case, Criteo, we chose not to do that, because at the beginning we had a small Vertica cluster compared to a very big Hadoop cluster, like the first one in Europe. And so we decided to do all our data transformation in Hadoop using various MapReduce frameworks initially. So like cascading, scalding later, and Hive for the most simple things. And so what we do is like we do our transformation within Hadoop. And then to load Vertica, we embed their native client within Hadoop streaming jobs. And we create one job per Vertica node, and then we saturate the network and kill the DB with whatever we insert in it. And we're pretty happy with this pattern. The users that connect at the precise time, we load a lot of data or not, but we are happy. And so to use our C++ library, we just added Java bindings so that it can be used within the Hadoop Java environment, and that was usable. So we did some benchmarks against the Vertica's native implementation that I told you about, against like count distinct, like what happens if you're really counting the distinct values, but also against Druid. So why did you do that against Druid? It's because Druid, we use it as criteria for the application I showed you. So we have two versions of this application, one internal, one external. So one is using Vertica, another is using Druid. And Druid was chosen, one of the reasons to choose Druid was because of its ability to use HyperLogLog. So the figures that Pavel is going to present illustrate the difference between Druid and Vertica. One thing worth mentioning is that we don't pre-compute the synopses in Hadoop. We wanted to do some kind of fair comparison between the products. So we use in Druid like online computation of the synopses, which is not recommended, but Pavel will insist on that. So that's, let me give you the mic.
Okay. Yeah, so you might think, okay, so how this creepy stuff performs? And first, here's our setup. So, we really tried to make this comparison as fair as possible. We had two identical clusters for Druid and for Vertica. So we used 7 HP Gen 9 servers with those 2 sockets, Xeon E5 2630, low power, Haswell, 256 gigs of RAM, and 6 SSDs per node. Basically, we were using CentOS 7.2, but we updated this prehistoric kernel to something more recent. So on both clusters, we used RAID 0 for the array of SSDs. In terms of the versions that we used Vertica 7.2. You might think, oh, but this is prehistoric and it's like 2 versions behind what you can download now from the Vertica page, and this is true, but this is what we use in production. So to make it even more fair, we use also a prehistoric version of Druid. Okay, so this is three major versions behind. I think now it's 0.10. You can download Druid 0.10. But to make it at least a bit fair, we had exactly the same hardware setup. Actually, on the Druid cluster, we had 9 nodes, but 7 worker nodes. On Vertica, all the nodes are worker nodes. So basically, this is the same CPU power and the same memory on both clusters. Yeah, because you might think, but this guy works for Criteo and Vertica sponsors the conference. So of course, these guys want to show that Druid is rubbish. No, I really wanted to make this comparison as fair as possible. So in terms of hardware, this is it. In terms of the OS, it's also the same. In terms of the versions, we just use what we use in production. Okay, so in the Vertica numbers, you will see actually 3 things. You will see distinct count, the accurate one. You also see Vertica native implementation. There's actually 2 steps. First, you create the synopsis from a column, and then you calculate distinct count from that synopsis. So in our implementation, we mimicked exactly the same thing. We have 2 functions, and we calculate that in 2 steps. In our implementation, we had 2 parameters. We had precision, so number of bits we take from the hash function to create buckets. And we also have this serialization format, so we can change whether we use 8, 6, 5, or 4 bits to store a bucket. Yeah, and to run this test, we generated a table with 30 columns, so rather a wide table. And we had two data sets, one small and one large. The small one we used to compare to Druid. The thing is, we couldn't work on the larger data set because even for the smaller one, it took 13 hours to load that into Druid. So for the larger data sets, it would take days. So in the end, we stayed with a small data set. The larger data set takes around 700 gigs compressed in Vertica. So you might get an idea how big is that. We didn't do any joins because in the end, we just generated a white table and there's no point in joining different tables because in the end you will get the same thing. And we don't want to benchmark joins. So before I go to the execution times, first I show you resource usage. So as you can see in the legend, there are actually a couple of implementations. There are Kritos, there is Vertica, HyperLogLog, there is native, but here you see only two curves. That's weird. But actually, the native one is this one, while all the other ones are hidden here. So in terms of memory usage by node, the maximum one is roughly the same. So you don't see significant differences. In terms of network usage by node, it's actually the same thing. So you have native, distinct count, and you have all the others that use roughly 0. Okay, we can say they don't use network. Okay, now the more interesting part. So this is a Vertica native distinct count. If you read the Little Prince, you might think it looks like a snake who ate an elephant. And here is distinct count. This is the Vertica distinct count, and there come our distinct counts. So depending on how many bits we use for serialization, we have either this CPU usage, which is small because there is no bit twiddling. We don't have to really play with how we store those buckets, or it increases with the compression. So we might say here that we trade CPU power for storage. Okay, now the juicy stuff. So in this plot, you will see speedups where Vertica's HyperLogLog is the baseline. So these are actually speedup factors. So if it's 1, it's the same as Vertica's HyperLogLog. If it's higher, it's better. So here on this column, I don't know if you see that, it's 16 bits of precision and 6 bits for serialization. We are actually worse than Vertica. Okay, I didn't see we are geniuses, but we just to show, to make it fair. But actually, if we play a little bit with the parameters, we can be as fast as 1.5, 1.6, depending on the data we choose. So here we have 2 columns. The count is around 490 millions. One is sorted, one is unsorted. So you can see maybe it's not that straightforward, but for sorted, we actually have some gain with respect to the unsorted column. And here we can see some other columns. So we have floats, 5 million. All of those are unsorted. Float, 5 million, string, 3.5 million, and float, 900K. So in all those cases, we are better than Vertica HyperLogLog. Okay, now we actually have the same data, but we added count distinct in the mix. So now count distinct is the baseline. It's just to show you that when you compare Vertica HyperLogLog, which is this color here, is 10, 15 times faster than the distinct count. Well, depending actually on the column, it can be twice as fast, but it really depends on your data. Okay, so this is like the worst side of the thing. So our accuracy is not as good as Vertica's. Again, it depends on what you have in your data and how random is that, and whether it's string, float, whether it's sorted or unsorted. But Vertica stays around 0.5% of the error, while we can go up to 1.2, 1.5, even 2%. So it's also a trade-off. You have, when you use this or the other implementation of HyperLogLog, you have to decide whether this accuracy is really important to you, or you prefer speed and storage. So as François said, to compare apples to apples, we choose to use Cardinality aggregator in Druid. I don't know if you're familiar with Druid. So you have different Cardinality aggregators. This one is called like that. So in the documentation, it actually says, this aggregator will be much slower than indexing a column with the hyper-unique aggregator. So probably if we use the other aggregator, we would have different numbers. But since in Vertica, we have raw numbers, and then we do the both steps at once, and we time that. We want to time the same thing, roughly the same thing in Druid, so we use the other aggregator. If there is someone from Druid in the audience, speak now. Okay, good. Yeah, as I said, this is work in progress. This is tentative. This is, no guarantees. We just got these numbers. We present them. We think the comparison is fair, but of course, there might be someone who thinks it's totally unfair. So here, the baseline is Vertica, HyperLogLog. So those orange columns you already saw in the previous plots. The blue columns are Druid. So Druid is, 5 times slower than Vertica native HyperLogLog, while we can go, up to 1.2, 1.4. It's depending on the data. So we also have to say that here we only use strings unsorted. So it might be different if we use numbers sorted. We didn't test that. And this is for accuracy. So here and there, you actually don't see anything because we don't have an error. We just give a precise estimate. The blue column is again Druid. So, Druid is even worse in terms of accuracy than we are. It's 2%, 4.5%. It depends on the data. François?
Thank you. So what's the current status of that? So we've proven to be able to be faster than Vertica's implementation, because what Pavel mentioned is that we suspect that Vertica is using like a 16 bits of precision, which is great to be precise, but I mean, we can be faster than them if we lower the precision while still being accurate in our notion of accurate. So ours is configurable, so I think it's better. And we proved, I don't know if we proved, but we discovered somehow that we are faster and more accurate than Druid's equivalent implementation in this case, which is creating the HyperLogLog synopses plus computing on top of that within Druid. Our implementation is also usable in Hive, which is pretty cool. And it's been integrating in a production application named Opera. But all of this is still a work in progress. To be very honest with you, we're still like writing down some slides yesterday evening, trying to do some benchmarks. So it's not totally finished. So one of the things we wanted to do, but we don't have time to do so, is like compare figures on the already computed synopses in Hadoop. But as Pavel said, since it takes a few hours for Druid to recompute a column, so I mean, when we discovered that we didn't do a hyper-unique column, it was 20 hours more computation to have that. So, and since they didn't want to move the conference from us, so we didn't have the figures. We want to do these comparisons, like computing, like the synopsis computation in Hadoop, having a look at the figures and compare that afterwards in the engines. So compare us to the Hadoop indexer. We want to play with more data, which is my boss demand, because we pretty much know that with millions, hundreds of millions of rows, HyperLogLog is pretty good. But the performance we discovered in the past, that when you reach like the hundreds of billions, this starts to eat a lot of CPU to get into more trouble. So for that, we just need to import more data, maybe play with a bigger cluster. But since Neil Thombre has written the no-sum data generator written in Go, and you can do whatever we want. As you've seen, as you may have noticed in the presentation, reduce the synopsis serialization format it did not lead to the optimization we initially thought. I mean, we thought that by reducing the size, like the computation would be much faster, and it's not the case. We need to figure out why. And our CPU consumption for the same synopsis size is still way bigger than Vertica's. So there can be an explanation, which is we are using their external SDK, and so their internal SDK might be better than what we do, which is possible. And we're going to have a look at that. So we already open sourced like the UDF, as I told you. Also, Neil kindly put his data generator on the generic thing that can generate many columns, many cardinality, whatever you want, in GitHub. So which is this is the URL. And we'll also, of course, put somewhere on GitHub like the raw CSV files of the metrics we got for the benchmarks, and we'll wrap that up within a post on Creature Labs blog, something like that. In the near future, we just need to be finished with all our benchmarks. So, thanks a lot. Sorry, I'm maybe a bit late.
So if anybody, I imagine there might be a few questions. I just want to reiterate what François and Pavel were saying. These are preliminary numbers. I know, the idea that an on-disk database is, an order of magnitude faster than an in-memory database seems a little bit odd. It's important to take away the qualifiers that were presented there, and that we're going to keep working on this to get to the bottom of that dilemma. So, without any question there.
K-mean values. So did you hear me? Sorry.
Yeah, can you say again?
Sorry. Did you consider other sketching methods than HyperLogLog, like K-mean values, for instance, or other sketching methods?
I can take this one if you want. Sure. Initially, not really. In fact, we know what K-means is, of course, but the thing is, we've been using HyperLogLog on the Hadoop side for quite a while. And like the idea at the very beginning was like just to see, it was like just an experiment. Like, can we put that in Vertica and does it work? So, and since it brought like the accuracy we're looking for, don't look that much further.
No, because I think K-mean values has other interesting properties, like you can merge two sketches to do an intersections of sets, things like that.
Yeah, that's this property is interesting for all use case. That's not necessarily the thing we're looking for. So, but yeah, I mean, we're still looking into things. But we are huge users of HyperLogLog already before doing that.
Yeah, there is one there.
Just seeing if you want to climb the stairs.
So thanks. Quick question. So you buy a lot of performance if you reduce the size of the buckets, right?
Well, it's just the opposite. Actually, we buy storage, but we spend more CPU time, a little bit.
If you increase, right?
If we have less bits per bucket, we need to do some bit twiddling, and then we have to pay in CPU time, but we buy storage.
Upon query time, the hope is that if we compute that on Hadoop side, the computation is longer, but then afterwards, like getting that at query time, we hoped it would have been better. The truth is, like from other benchmarks we did that are not in there, like if you split the thing in two, the thing we want to do, like on query time, even if you serialize that, it's very small, like it's twice smaller than 8 bits. It doesn't bring like the speed. So we think that there's something in like the deserialization code or something like that that brings some complexity.
So I guess my question was, if this is possible to tweak, what are your recommendations for users to use? I guess if it's an option, what do you suggest people to use?
So if you can shift the computation, the synopsis creation to the biggest cluster in Europe, biggest Hadoop cluster, then just do that. Otherwise, I think you can use this very conservative 6 bits per bucket, and this would be the best option.
Thanks.
Maybe time for one more. Okay, in the back. Let me run.
Run, Forest.
Okay, so excuse me. So, what's the gain of time against a regular Hadoop job when you try to count how many user IDs there are in the data lake?
In fact, the gain of time, because in the end we're going to be computing the gain of time. I even think that it's going to be worse. The powerful thing it brings is that, for example, let's imagine you have ingested your data with this vector instead of a pre-computed distance count. Then you have your crazy product manager that wants you to design an application that allows users to drag any kind of fields, that to do any kind of distance count of user IDs per particular column. Then you can do that. I mean, you have this vector; it can be combined by pretty much every combination. So of course it costs a lot to compute at the very beginning, but then it brings some associativeness within your front end, which in the contrary, of course, computing one count distinct, yeah, it costs less. But in the end, if you did 20 different group bys, it costs a lot.
Yeah, so actually we have an application, that uses those data. And of course, we cannot have Hive jobs behind that, so we have to have something really responsive and fast. And also in terms of resource usage, this HyperLogLog algorithm uses much less resources. And also the other nice thing about that is that you can pre-aggregate. So you can aggregate and then aggregate again, while when you use distinct count, you only get the number, and there is nothing you can do about that. You just get the number, and you cannot aggregate even more.
Okay, yes, thanks.
Okay, with that, I think we will go have lunch, I think.
Bon appétit.
Thanks.